Hello, everyone. So this is the first tutorial session on Agda as part of the HoTTEST Summer School in 2022. And I'd like to start by giving what I call my favorite example in type theory. And this isn't directly related to Agda, but it's something that I think will serve as a motivating example and something that we're going to try and understand. And it's going to take several lectures before we can fully understand what's going on. So 2 summers ago, I taught a course in type theory. And I started off this course by introducing proofs. It was actually an intro to proofs course, not a type theory course. Can everyone see my screen? So I wrote notes for this, and I start off with the natural numbers, and I ask, what are the natural numbers? Well, the natural numbers are the definite answers to the questions of the form, how many apples are there in this basket? And then how do you tell how many apples there are in a basket? Well, you start from 0, you iteratively remove apples, and then you increment your count. So in other words, you can count to any number starting from 0, barring boring objections like you can't fit 1,000,000 apples in a basket. And then I go on to define a more formal version of natural numbers, which are these numerals in successor and 0 form. And then I come to the problem of defining addition. And from here, I pulled up a quote from a book by Morris Klein, written in 1973 about new math. And so the quote says, "Let us look into a modern mathematics classroom. The teacher asks, why is 2 plus 3 equal to 3 plus 2? Unhesitatingly, the students reply, because both equal 5. No, reproves the teacher. The correct answer is because the commutative law of addition holds." And so then I go on to say, well, what is the most useless answer that you can give to a question like, what is 5 plus 13? And you can say 5 plus 13 is 5 plus 13, or it's 13 plus 5, or it's 7 plus 11, or you can say it's a number, or you can say it's greater than 2. And so that's sort of losing a bit of a point. You can ask more pointedly, what is the value of this? But then you can say the value of 5 plus 13 is the value of 5 plus 13. Or as one of my students said, the value of 5 plus 13 is learning how to add. But the most pointed question that you can ask is evaluate 5 plus 13. And that's not so much a question as it is an order. And I think that there's no answer that can escape that question without being correct. No correct answer can escape the question with evading it. And so then I wrote some absolutely throwaway remarks. And the absolute throwaway remarks are that in the Apple model, the meaning of 3 plus 5 equals 5 plus 3 is that if you first count the 3 baskets and add that value and use that value as the starting value to count the 5 basket, you would get the same number as you would had you interchanged the baskets. For numbers, then, the meaning of 5 plus 13 equals 13 plus 5 is that both sides have the value 18. So we see then that the commutative law of addition states that for all numbers n and m, the value of n plus m is the value of m plus n. In our setting, this law cannot be stated without reference to evaluation. However, the equality 5 plus 13 equals 13 plus 5 may be seen through direct evaluation without invoking commutativity. In other words, Johnny was right. So what I did there as throwaway remark was suggest that the arguments, because both equal 5, is a more fundamental argument than because the commutative law of addition holds when it comes to answering the question, why is 2 plus 3 equal to 3 plus 2? Right. And so this is a throwaway remark. There's certainly no way that we can make this into something rigorous, is there? And so what was the point of the course? The point of the course was to put math on a computer. So the students wrote their own proof assistance. So this isn't Agda, this is a homebrew proof assistant. And in this homebrew proof assistant, we've put math on a computer and we prove the commutative law of addition. Here is the commutative law of addition. Now, there are some commands that I can run. One of the commands is, and let me make the font bigger, check one. So check is going to type check something, and I'm going to put in the name pluscom. So pluscom is something that I've defined, and I'm going to ask what its type is. And this is going to tell me that the type is for all natural numbers n and m, n plus m equals m plus n. So it's a proof of the commutativity of addition. Now, what I'm going to do is, how about if I specialize this statement just to the numbers 2, written as numerals, and 3? Well, if you do that, then it's a proof that 2 plus 3 equals 3 plus 2. So in particular, this statement right here is an expression for the proof because the commutative law of addition holds when answering the question, y is 2 plus 3 equal to 3 plus 2. Now, what I'm going to do next requires a bit of motivation. Imagine that you have a book like Bourbaki's analysis. And so the idea is that everything is supposed to be founded in terms of primitives introduced to the set theory volume. So if you have some proof there, you can recursively expand every lemma and recursively expand every definition until you get just to the starting points. But if you do that, it's going to exponentially blow up because you're doing exponential expansions at every single stage. And so it's going to be a huge wall of text. And for a human, doing all of that expansion would be prohibitive. It's just too complex. But a computer can handle that just fine. So what I can do is I can take pluscom and I can normalize it. And I'm going to get some expression in pure logical primitives. So reduce 1 pluscom. This is the proof of the commutativity of addition expressed in pure logical primitives. And now what I'm going to do next is sort of pretty direct. I'm going to take the proof, because the commutative law of addition holds, in the special case of the numbers 2 and 3, and ask, well, what does that reduce to? And it can only be one thing. Does anyone want to guess as to what it will reduce to?
Yeah,
so someone said
5 or something.
Yes. And what did Johnny say to the teacher? Johnny said the line, because both equal 5, right? Reflexivity 5, because both equal 5. So what a computer has just done is it has taken a wall of text, if it plugged in some numbers, and then by a calculation, it has scientifically determined that Johnny's answer was more fundamental than the teacher's. And what's cool is that not only is this true for this particular proof of the commutativity of addition, but for any possible proof of the commutativity of addition, you'd have this reduction. And in fact, it's because of an underlying meta-theoretic result that in Martin law of type theory, any closed proof of equality is reflexivity. But in HoTTEST, that meta-theorem doesn't hold. But in HoTTEST, we can show that natural numbers are a set. And what this essentially amounts to is saying that there's just no deep way in a provable way to prove that 5 equals 5. And I think that's a really good motivating example, and you should keep that in mind when working with proof assistants. Now, let's get to Agda. Okay, let's see. Here we are. Any questions about that, by the way? Oh, is this someone links a paper? Is this going to be Prabhakar's paper? Yes, it's Prabhakar's paper. This is Prabhakar's proof assistant, in fact, that I'm using. So it's a meta-theoretic statement in Martin law of type theory. And the meta-theoretic statement, the question was, what is the law that does not hold outside of MLTT? It is the statement that any closed proof of reflexivity of equality is definitionally reflexivity. And I can write a link to, actually, Prabhakar has a set of notes which teach you type theory. And it's how I originally got into type theory, by writing your own proof assistants. And I recommend it very strongly. Okay, I will put that in the chat at the end of this lecture, and I'll also put it in the Discord and in the YouTube video description. And I really am fond of those notes, so I'd be happy if you took a look at them. Okay, moving on to Agda. So what I'm going to start off with is I've opened the exercises, and a cool thing that you can do in Agda is that you can do split views, in Emacs. So here I have the screen split. This is a literate Agda file, so it's markdown mixed with Agda code. Here I just opened a regular Agda file, and you can see at the bottom that the file is named, and I'll make the size bigger a bit, solution.agda. And because it's 01-solution, I have to name my top level module the same thing as I've named this. And what happened is I went to the link on the website, and I downloaded the zip file that Amy provided. And then in the directory where I had the problems, I just created a new file for the solutions, and all of the imports worked. There is this import prelude, and it is actually part of the code that's included. It's not part of the standard library. Screen isn't showing. Do people see Emacs now. Good. Right. Now I'm going to teach you something really cool. So for example, what is prelude? Well, I am going to put my cursor on this, and then I'm going to hit meta and the period. So if I hit meta period, it's actually going to navigate to this page, which is prelude. And if I want to go back, I'm going to hit meta comma. So this is how you can navigate between your Agda code, treating it as a sequence of hyperlink references. So let's look at this not is involution that we decided to hide from the import. Well, its definition is here and my cursor is already there. Let's go back. Let's go to prelude. Let's see what we can have here. Well, for example, there's a notion of identity types. Let's look at the definition of identity types. Here they are. I can go then press meta comma to go back twice, and I'm back at my homepage. So isn't that cool? Emacs lets you navigate your Agda code as though it's a hypertext library. What is meta? So the way that Emacs works is that there are two main keys that you press to run commands. They are control, and then there is meta. Meta, if you usually you have to bind it to something. So for example, I use OS X, and there is an option to let meta be something, and that might be in Emacs somewhere. But for me, meta is the option key on Mac. But you might have to configure that. Like meta isn't a key that's labeled on a keyboard. Okay, let's get started. So let's look at what the exercises are. And the first exercise is that we have the Booleans. What are the Booleans? Well, I'm just going to press meta dot, and we can see that the Booleans are an inductive type with two constructors, true and false, right? So let's go back. And here, let's define this exercise. So I'm going to define a infix operator, and its type is going to be bool to bool to bool. And then I can load this, and it'll just tell me that there is an error in that this hasn't been defined because I haven't given it a definition. Okay, so let's give it a definition. So let's say what it means to take B with and it with S. And I'm going to put a question mark here, which is a hole, and then I'm going to reload the file, which is CCCL. And so you see there's a hole there, and I can ask, well, what am I supposed to define? I'm supposed to define a Boolean. That's the goal. And I'm working in a context that has S and B as Booleans, right? Now let's look at the problem statements. The problem statement is to define this by pattern matching on both arguments, whereas in the lecture, we defined it by pattern matching on the leftmost arguments. So I'm going to take B, and then I'm going to case split on B. And what I do to do that is I press CCCC. Oh, also, Amy, can you handle the questions in chat and tell me if anything important comes up? Right, cool. Then the idea is that we want to case split on both arguments. So I'm also going to case split on S here. I'm going to do the same thing, and it's going to split that line into two lines. And then I should also split it here into two lines. So now I have four cases, all possible combinations of true and false. And should only be true if both of its arguments are true. Isn't that right? So in this case, true and true, the answer should be true. And then this is the most satisfying command in all of Agda. It's the give command. When you have a hole and you want to fill the hole, you press C space. And then the hole goes away. And it's just so satisfying when you do that. And then, as we said, if one of the arguments isn't true, the rest of the arguments should be false. So I'm just going to copy that over, and then I'm going to fill all the holes. Bam. Now, exercise 2 is similar. There's exclusive OR. So does anyone want to see that, or should we move on to a more interesting example? I think the exponential is slightly more interesting. So let's define an exponential on natural numbers. And so the way that I'm typing in the natural numbers is I'm typing in \bn, capital N, for Blackboard N. And so this is supposed to be n to the power of m. Now, let's just see what we have defined already. So I'm going to use this command, meta dot, to just jump to the definition of the natural numbers. So it's in the introduction module. And let's see if there's anything that we have. Do we have like multiplication, for example? We do have multiplication. So let's look at the definition of multiplication. It says structurally recursive on the first argument. It says that 0 times y is 0, and that the successor of x times y is x times y plus y. So I'm going to go back, meta comma. And then let's think about this.
What was what was the symbol that they used for 0 on the right-hand side of that equation? Was it just 0? Just the numeral?
Just the word 0. We can look at it again. So
no, on the left-hand side
the
of
word.
0. Whenever
Sorry?
you define multiplication.
Yes. Here it is.
Just the numeral 0 on the right-hand side?
So what's happening is, in order to define this, I can show you how you define it. You're trying to define what it means to multiply x and y, right? And how we're going to define it is we're going to define it by recursion. And we're going to define it by recursion on the first arguments. So when you case split, it automatically goes to these two cases. And then the question is, how do you handle these two cases correctly? Oh, you're asking, why is there a 0 here? I see what the question is. The reason is that there's also a built-in way to use decimals to represent numerals. So I could have equally well put a 0 here. And this notation, I was going to claim it desugars, but apparently the system treats it in a slightly more efficient way. So yeah, I could also write 0 here.
Okay.
And that's how the case split will automatically work, but you can also use numerals.
And you could put 0
so
on
maybe
the
this is more clear.
too, of course. Yeah, okay, cool.
Oh, why do I keep trying to change the screen? I just press meta comma. Okay, so if we're defining exponentiation recursively, should we split on n or m? M, because if you think of what, for example, m squared is, n squared. N squared is n times n, right? So the 2 breaks down to become an iterated product, but it's not like we do induction on n, we do induction on m, right? Does that make sense? Anyone want to ask why?
I think I understand why that would be the better option, but could you do it the other way or no?
I don't see a natural definition. There isn't a natural recursive definition.
Yeah.
I mean, you could first split on n and then on m. Sorry, I might have spoken over you. What did you say?
Oh, no, I said I see why it's more natural for sure. So I understand.
Good. So if you exponentiate anything to the power of 0, what should that be? Even 0 to the 0.
Controversial question.
Not a controversial question. In combinatorics, you can think of n to the power of m. It should be 1. You can think of n to the power of m as the number of functions that there are from the set of m elements to the set of n elements. And there's exactly 1 function from the empty set to the empty set. So I can write 1 here and I can fill that hole and it's happy, but that might be slightly confusing. So I'll just write suc of 0, successor of 0. That's another way to write 1. Okay, and now recursively, if we're taking n to the power of m plus 1, how do I write that in terms of n to the power of m? So we're going to use this, right? Okay,
You
let's
should
see.
really
Chat
buy
is
a
saying,
second
yeah,
monitor to keep an eye on chat. Yeah, they're saying it's n times n to the m.
right. Yeah, please, please do let me know if things come up in chat. Thanks.
Sure.
I'd be grateful for that.
Sorry, yeah.
So we multiply by n, right? So we have one more additional multiple of n. Bam, fulfilled.
Actually, yeah, sorry, Astra, can we go
Mhm.
back? There was a question.
Yep.
Ryan says that the definition of and prime sort of makes him think of a non-short circuiting and operation. Is there a real connection there, or? I think in an earlier class, somebody said that we're using with call by name evaluation. So maybe short circuiting isn't a thing, but is there a way in that this is a useful comparison? And that's
This
Ryan's
is actually
question.
an excellent comparison because if you think about it, there are different computation rules for both definitions. So let's see if the operation and is defined. So I'm going to press the combination CCCD. And this at the bottom is going to let me type something. I'm going to try and type this and see if it's already defined. And it'll give me a definition. So that's the definition that's defined in class. And then I'm going to press CCCN. And then I'm going to consider the expression, let's say true, or let's say false. And then actually, I want to put this in the context of something. So let's say we have foo, which is a function from bool to question mark. And so this is going to be an Agda trick. The point is that since I'm defining a function from bool to whatever, this function can take a b argument. So that lets me operate in a context in which I have a bool available. There's another way to do this. I can write postulates, b and bool. And then if I type in foo equals question mark with no type, I'm still working in a context in which I have b defined, although it's not going to display it here. Now I can consider the expression false and b. And now I'm going to press CCCN to normalize that expression. And you can see that that reduces to false. So it short circuits. It doesn't evaluate the b expression at all, right? Now let's instead put that over here and use the false, this definition. And if we normalize it, we see that that's normal already. You can't reduce it because it only computes if both arguments have been evaluated. So this is indeed a non-short circuiting definition, while this is a short circuiting definition, and there is a distinction in how they are defined in type theory and how they behave with respect to reduction. Okay, so hopefully that answers that question. Good question. Thanks for transmitting it to me. Okay, and there's also an example. When we have definitions defined and they compute and you put sort of definite numerals inside of them, you can reduce things. So let's just consider this. We're supposed to prove an equality between these two things. Now, this is the triple equality, which means that this is the built-in equality inside of Agda. So, well, I mean, we're not using the library version. We're using the version that's defined in Prelude. So if I go to here, you can see that it has a constructor reflexivity x, because both equal x is what this says. And if I look at what the goal is, it'll tell me, so if I press CCC comma, that will show me what the goal is. And so the goal is to prove 81 equals 81. Well, that's already reduced. What I can do is I can preface CCC comma with 3 instances of CU, and this will give me the least amount of normalization that Agda is willing to do. So if I press CU, 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 CC, C comma, it'll actually give me that the goal is 3 to the 4 is 81. But if I press CCC comma, it'll do some computation and simplify the expression. And so just because the definitions are built into the type theory, the definitions compute, and it looks like we're trying to prove 81 equals 81. And why is 81 equal to 81? Because both equal 81, right? Okay, now I think the list example is cool. So let's look at lists. I'm going to look at the definition here. And what lists are that they have two constructors. There's an empty list, and then there's a cons operation, which conses on an element at the front of a list. And the term cons is short for construct and is from Lisp. So going back, suppose that I have a list and I have a function. My function is f, my list is x's. The idea is that the function is between two types, x and y, and I want to write a function that takes a list of x and returns a list of y. Now, morally, how do I do that? Well, I apply the function to every single element of the list. How do I do that? I do that by recursion on the list. So what I'm going to do is I'm going to take the list x's and I'm going to case split on it. And so there's a case for the empty list, and there's a case for when the list is a cons of something with something. Now, if I'm just trying to map something onto the empty list and I apply f to every single element of the empty list, what list do I get?
Empty list.
Good. So I just type in the empty list here, and then I press the list satisfying command, CCC space, and bam, it's filled. Now, here I'm going to use a recursive call. So I am allowed to use the definition of what mapping f onto x's is in the course of defining this. Right? Now, what should I do with this expression as well?
Is it return a list, I'm assuming?
I mean, so technically, by the way, since we're returning a list of y, and this is a list of y, this definition is perfectly valid, but it's wrong because that's not
Right,
what
we need to
map should
concatenate
do, right?
it with the first part of,
Yeah,
so f of x.
f of x. So we cons f of x onto, and by the way, I could put parentheses here, and that would work. Sorry, let's just look at what the list constructor is. Whoops.
I think
it's
it's
two?
normally, I think it's two
It's
ASCII
two.
colons.
Okay. Sacrilegious, in my opinion.
Martin has his style.
Yeah.
So
we
the
can
map
also remove
thing,
these.
I'm sorry.
Sorry, go ahead.
What does the map thing do? I've not seen that before.
So the idea is, suppose that you have a list of, let's say, numbers, right? And suppose for every number, you have a function that turns the number into a string of that many copies of the letter A, right? So this is a function that takes numbers and produces strings. Now, given a list of numbers, how do you produce a list of strings? Well, you apply the function to every single number in the list, and then you get a list of strings, right?
Right.
So that's the idea. And when you're doing functional programming, this is a very useful function that is going to come up very often.
So just to reiterate, map f of x's takes every element of the list x's and returns f of the elements. Is that?
It returns a list whose elements are f of the elements of the starting list.
Yes, that's what I meant to say. Yes.
Good. Very good. Oh, now we're going to do a pretty interesting example. There's another higher order functions on lists, and that's the function filter. So suppose that we have like a function that is even, that returns yes or true if a number is even and false otherwise. Then suppose that you have a list of, let's say, numbers. How do I produce a list with only the even numbers? In other words, only the numbers satisfying the predicate that I provided. And so we're going to use a pretty interesting Agda construction in order to accomplish this. So what are we given? We're given a predicate P, which is a function from elements of X to Booleans, and then we're given a list of elements of X's, right? Now, fundamentally, we're going to define this by looking at each element, right? But how do we look at each element? Well, we get elements by sort of breaking the list down by recursion. So we're going to have to case split on X's, right? Now, if we're trying to filter out all of the things that don't satisfy the predicate out of the empty list, well, when we filter out all of the elements of the empty list that don't satisfy the predicate, what list do we get?
The empty list.
Exactly, because there are no elements to filter out. So that's good. Now here, basically, we can filter X's with respect to P. But then what do we do? What we're going to do is going to depend on whether P of X is true or false, right? So if P of X is true, then we want it inside of the list. If P of X is false, we don't want it inside of the list. Now, how do I split on that? Well, I'm going to use what is called in Agda a where clause. Sorry, a with clause. So I'm going to say with P of X. And then the notation for this is, well, I can do several things, but I can also put in triple colon and bar. And then I can put, let's say, Y equals to question mark. Now, what does this do? So if you look at the context, then Y is a Boolean. So what happens is I consider this expression and it's a Boolean, and then I'm going to bind it to a variable Y. So with P of X being Y, right? So I've added Y to my context. Now, what's the utility of this? The utility of this is that I can case split on Y. So in order to make this definition, it suffices to consider the case when P of X is true and when P of X is false. And then if I know that P of X is true and false, I know what to do with it. So let's suppose P of X is true. That means I want to keep it in my list, right? So I'm going to take X and cons it onto the recursive call. And what's the recursive call?
X's.
Yeah, I didn't hear the first part of it.
Oh, I just said X's.
Well,
Jared in
no,
chat
not just
says
X's, because then
filter
what
P
you've
of
done is,
X's.
yes,
Filter
filter P of X's, because you need to filter the rest of the list. It's not like you just
Right, right,
stop looking
right.
at the rest of the list when you, yeah. Cool. And now let's suppose that X is false. So we don't want X anymore. So we just return the recursive call without X at the front, right? And so this is this with abstraction. And there are sort of, you don't need to put a triple dot here. You can also represent these arguments again. And you might even case split in one of the cases. But I'd recommend looking at the Agda manual if you need a case that's more complex than this of using with. But remember, what I basically did is I started off by putting Y here, and then Y was just bound to whatever P of X is. And then this let me split on what P of X is as being either true or false. And then I get to make the definition in the case that P of X is true and in the case that P of X is false. So that's called a with abstraction.
I had a question.
Yeah.
Can we do this without a with abstraction using where? Is it?
Yes, we can. So that's what Martin did. I personally do not like it as much, Martin's approach, but I guess maybe I should demonstrate that as well. So I am going to define a function filter prime. And now so the question is, what helper lemma do I want? Well, I'm going to produce a function that, given a list and given an element, adds the element or not to the list depending on whether it's the relevant, whether it satisfies the predicate. So I'm going to call this decide.
Call it go.
Go. Sure.
Real Haskell.
Yeah. Oh, nice. So go is going to take what is it going to take? Well, let's say I already have X is bound. Sure. I'm going to take list X, or let's say I'm going to take P, the predicate, or the predicate's already given. I'm going to take X and I'm going to take list X and I'm going to return a list of X. Now, I have the element X and I have my list X's, and I'm going to either return.
Sorry to interrupt. You'll have to add the binding for the implicit X if you want to apply the predicate, or if you want the code to be scope correct.
Oh. Oh.
Yeah, you have to add a. No, on the left-hand side of filter prime.
Ah, yes. Oh, of course, of course. Okay, sorry, that's clear. The reason is that add these arguments, they're just names in the type, right? The type sort of, they're only meaningful when they get bound, because I didn't have to write X's here. In fact, the name X's didn't exist here. So the name is only meaningful when it's bound somewhere. And this where clause is something that applies to the right-hand side of this equality. And the right-hand side of this equality, the context is determined by what's on the left-hand side of the equality. Thanks, Amy. So in order for X to make sense, I have to give it a name, right? Because the signature doesn't give it a name. It's only here where I actually introduce bound variables into my context. So in this case, X is just a thing. Actually, well, okay. So, but then it looks like we'd want to do it with abstraction again. So in fact, let's make it so that it takes a Boolean, and then it takes an X. And then, in fact, I think there's an even better abstraction. Let's say that we want to define a function go that takes a Boolean. And then let's say that X and Y are types. So here is a nice abstraction that I can make. Let's say X and Y are types, and I have a function f from X to Y. Sorry, from X to X. You know what? I don't even have to define it in, okay, fine. Never mind, I'm going to keep X here. No, I'm not going to keep X here. X is a type if I have a function from X to X. And I'm given a Boolean. And I'm given an X, then I'm going to get an X. And what it's going to do is it's either going to apply the function or not apply the function. Based on, I think maybe a more natural set of arguments would be this. This is an abstraction that I like. So I'm going to case split on the Boolean. That if the Boolean is true, I'm going to apply f to X. And if the Boolean is false, I'm just going to return X. So this is a well-typed definition. In this case, I'm going to use it on the type list X. And the function is going to be consing on X. So this is a level of abstraction that I like. So I'm going to go, and I'm going to consider the function. Well, so here I want to actually case splits on X's. So here we are done. And here I'm going to add the where statement that we had before. So the reason that I'm not using the old X is because the function is going to be from lists to lists. So maybe I can even call it Y to just remove any risk of confusion. So I'm going to say go. The function is going to be consing on X onto the list. Now, if I want to sort of turn this into something where I filled an X in the first slot, but the second slot is still empty, I can put an underscore here. So that's a third use of underscores. And I can show you a different way to write that. And now the list that I'm going to consider is x's, and the Boolean is going to be p of x. Now, another way that I could write this is I could consider the function lambda y's to x colon y's. So let's look at this abstraction. This abstraction either applies a function y to an element of y or not, depending on whether the bool is true or not. And this is a level of abstraction that I like. So, okay, there are a bunch of questions in chat. Is there anything relevant?
No, they're just making fun of you for changing x to y to reduce the confusion, but still calling the variable x. Now you have an x of type y.
Good. Thanks. That's also clear. Okay, I think this was a really good question to ask about writing it using where, because the question it was, what level of abstraction do we use? And it turns out that for me, this is the nicest thing. I think this is really nice. Amy, what function would you have used here?
I would rather use the one defined in terms of width.
Right. But if you were writing it in a where statement, because I use this type signature.
Oh yeah. It's a good question. I would probably define the eliminator for Booleans if I had to go that general and then use that.
Fair enough. Yeah, that makes sense. But I won't literally do that right now as another example, because let's move on to something else. So, and here's an example with filter. So is not 0. Let's look at the definition of is not 0. Sorry. Am I not?
Right
I
above
pressed
the
a command. Sorry.
No, it's going to the right place. It's
I
just right
see.
above the example.
There it is. That's what's happening. Makes sense. Thanks. Right. So we have this list, and then I should actually copy this. And then instead of, by the way, doing this example, I'm just going to copy this over. And you know what? I'm going to write foo equals question mark, right? And then there are sort of no variables in the environment here. This is an expression that makes sense in the global environment with all the definitions that we've made, right? And so I can just look at this expression, and what it is that there's an equality here. What this is that it's a list of natural numbers, right? And what list should it be? Well, we're getting rid of the zeros, right? So it should be 4, 3, 1 empty list, right? Now, one thing that I can do is in the context of this whole, I can press CCCN, and that normalizes the expression. So look at the normal form of this expression. It performs the computation and it finds that it's exactly that list. Now, in case you're wondering, the reason that we have this here as part of the exercises isn't just to get you to practice using REFL. It's also to check that your definition is correct. Because if your definition was wrong, then this would not fill the hole. And let's see if the filter prime definition works as well. It does. No, it looks like the filter prime definition did not, in fact, filter it. So there's a mistake with the filter prime definition. Let's see what that mistake is. So we're splitting on P of X. If it's true, then we're applying
looking at the wrong definition.
Oh, filter prime. Here we are. If it's true, we apply F, which is consing it on. If it's false, we shouldn't apply F. But
what is the list you are applying it to?
I think
I don't think a recursive call to filter.
Yeah, B of
we
X
forgot to make a recursive call. Good. Filter prime P X's. Thank you for not pointing that out. It's much more pedagogical when it's not pointed out.
Actually, several people pointed that out in chat, but
I
I
see.
decided to be annoying.
No, it's not annoying. This is fun. This is a good learning experience. So sometimes in type theory, Often when you're doing proofs, if the proof is well typed, then it's correct. But if you're defining a function like on natural numbers or on lists, then just because it has the given type doesn't mean it's the function that you want. So unit tests are useful in that situation. So this is a good lesson to learn. Yes, this was fun. How much time do I have? Let's see. Okay, 48, 12 minutes. Let's do some more interesting examples. These are good examples. I like these examples. Equality for Booleans in this triple version form. Okay. Let's do this exercise. The commutativity of and this is going to be the short circuiting version of and, not the version that we defined before. So the statement is going to be, well, let's just look at this expression and, well, what is it? I can press CCC dot, and then I'll have both the goal, which we don't know what it is yet because that's we're defining, and what we have. Well, the goal should be a sort in any case. That's a technical remark. So let's say for all Booleans, and let's make these arguments explicit. So B and S are Booleans. And then what I'm going to say is that B and S is the same. So I use the equiv, \equiv, is the same as S and B, right? And so given Booleans B and S, I'm going to prove this. And I'm going to prove it by induction. And when I do induction, I mean, B and S are basically symmetrical here. There might actually be one technical reason as to why we'd prefer to split on one or the other, but let's just split on B. So in the false case, well, it short circuits on one definition. So you can see that if we look at false and B, false and S, that just reduces short circuits to false, right? But the other side, it doesn't short circuit because it only computes on the first argument. And here, let's see what happens. So what we are required to show is that S is SN true, right? But once again, we can't split here. So let's split S in both cases as well. And in this case, the expressions will fully compute. So in every single example, we're going to have two specific Booleans, true or false, and it's going to be the same Boolean because the theorem is true. So because Y is true and true equal to true and true, because both equal true. So REFL true. Now, true and false is false, as is false and true. So both are equal false. Except when you can't type false. Now, this is sort of, I could type in REFL false again, but the thing is that Agda can sort of figure out what we want if we put something in here. So I'm going to put REFL underscore. And the unifier will see that there's a unique solution to this problem. And then I want to do something that I've never tried before. And I think that I heard about this for the first time in lecture. Apparently, if you press CCCS in a hole, the unifier will try and solve it in a unique way. Okay, but it doesn't normalize this. So yeah, it's false and false. Good job, unifier. Now, what happens if I append this command with CU? Look at that.
Would
So
CCCA work there too? The automatic.
Auto will also work. So let's see what happens if I do CCCA. Then it'll do this. Now, does CCCA, is it affected? What if I do CCCA? No. But if I do the CCCS, which is a general command in better, well, it looks like there isn't a unique solution. But in fact, there is a unique solution because both of these are definitionally the same thing. And so the point was that I put CU, CU, CC, CS, and then it actually gave me the normalized expression. So that's pretty cool. Okay, and here's actually two interesting examples. Mapping the identity and mapping composition. And I have 7 minutes, although I started 2 minutes late. So in fact, I have time to do both of these examples. So let's look at just, is the identity function defined? So if I go here, it's in a file. It's a polymorphic identity for all types A, implicitly A to A. Meta, comma, back to the definition. So if we apply the identity function to every single element in the list, then we get the original list back. That's the assertion. How are we going to prove it? We're going to prove it by what?
By induction. I'll just say it because otherwise
Yes,
you're going to run
thanks.
out of time.
Okay, so what happens in the empty list? Well, map computes on the empty list, right? So on the empty list, we're just required to prove that the empty list is the empty list. And why is the empty list equal to the empty list? Because both are equal to the empty list, right? Now here, map also computes on a cons list. So it'll apply it to the first element. And you can see that its IDX is x colon x's. Well, IDX colon the recursive call is x colon x's. But that's not normalized. So I can press CU, CU, CC, C comma, and then it'll just show me that I want X at the front. Now I can make the recursive call. I can try and prove this theorem in the case of X's. And if you see what I have, it's a proof that mapping the identity function onto X's is X's. But what I want to do is I want to prove that mapping quonsing X onto both sides, I have an equality between the left-hand side and the right-hand side, but with a function applied, and that function is cons X. And so what I'm going to do is I'm just going to look at prelude. And I'm going to look at some properties about equality. And one of the things that's proven in here is app, which basically says that if I have an equality, x equals y, and I have a function, then I can apply f to both of the things in the equality. I can essentially evaluate f on the equality. It lets me not evaluate f on points, but it lets me evaluate f on equalities between points. And so that's what we're going to use. We have what we want, except we want to change the left-hand side and the right-hand side by this. So what I'm going to do is I'm going to app onto this the function x. Now I'm going to use what I did before by putting in an underscore, and then these parentheses are all necessary. And then let's see what I have here. Well, okay, it's being slightly annoying because of this, but if I fill it, it fills. And then finally, let's do the example that we had before. So going back twice, I finally get to the example of map composition. And this is going to be pretty similar. So if I map G and F, it's the same as, well, I have to map F first and then I map G, because that's how function composition works. So this is also going to be proven by induction. And in this case, both maps compute. So why is the empty list equal to the empty list? Because both are equal to the empty list. And here, what we're required to prove is, well, this. Now, if I look at G composed F applied to X, and I just normalize that, it's just GF colon X. So if we think about this, and this is just a way to write G composed F, I can consider the recursive call. And that's basically what I want, except I want to add this at the front, right? So how do I do that? I do it using app. Bam. So really, sort of inductively, you just keep promoting the reflexivity proof that you started with. by just applying functions to it. But applying a function to reflexivity computes to reflexivity. So in the case of concrete lists, so if you apply it to a list that's not defined in terms of everything else, then it should just compute to reflexivity. But if you apply it to a list that uses variables, then it won't necessarily be able to compute. And wow, I got through both examples in time. So there were a bunch of other examples, but I think that I did basically all of the interesting things on this homework sheet. And I got to do my favorite example from type theory at the start. So I'm pretty happy about that. So I would encourage anyone to unmute themselves and ask any questions that are coming up now.
Astra, are you going to post a link to the your course notes for what was it, Math 250?
Thank you. So there's both. I can post these notes. This is just an intro to proofs. And then I can also post the notes of Prabhakar, which are actually full type theory notes. So the link that I'm about to share, it's only the notes on this intro to proof section where the goal was to get students to write their first proof. But I think I did a really good job there. And so, for example, if I share those notes again, except for the fact that screen share is, oh my God. So closed captioning on Zoom, you don't know what it does, but it actually does terrible things when you're in full screen on Mac. It interacts very badly with Mac's full screen mode. So I put in a lot of effort into these notes, so I'd be happy if people read them. Like there are 4 apples, parenthetical 4. And then later on, what this is secretly an introduction to operational semantics. Plus is sort of a computation producing construct. I motivate the way that we can define it by 2 specific formulas. This is similar to what we are doing in type theory. And then I write abstract syntax trees. This is an expression that's very hard to say for some reason. Abstract syntax tree. Okay. Abstract is easy to say, but if you're thinking that you're going to say syntax tree afterwards, for some reason, it becomes hard to say the word. And then there are computational traces in trees, and then there's a very rigid notation for writing proofs. So I think this is cute. Also, now you can see how many tabs I have open. Yes, this is the way I live my life. Here, let's post this link in chats, and I'll also post it on YouTube. But then there's one more thing that I want to show you, which is the cool thing, which is Prabhakar's notes, logic and computation intertwined. And sort of these notes weren't available on the web in public version when I learned type theory, but there was an internal University of Waterloo version of them. And this is what got me excited in type theory first. And these notes will actually, so they are structured around the question, so what is logic? And how do I put propositional logic on a computer? And then how do I put predicate logic on a computer? So the intro it's like short, but then there's a chapter on propositional logic, and you write your own type checker in Rackets. And Rackets probably the easiest language to learn, and Prabhakar links to Rackets tutorials as well. And then there's a section on predicate logic, which is essentially about dependent type theory. And originally this section was, I'd argue, unreadable. I didn't understand it at first. And then I taught a course on it. And then I sent Prabhakar a bunch of corrections. He was like, no, I like my version. And then my ex-advisor was using this in a summer course. When he got to this section, he stopped using the notes because he thought it was bad. And then Prabhakar relented and actually accepted my changes. So that's the story behind it. So right now, this is a very good chapter because it is now structured in a much more sane way. And I think it's a good introduction to dependent type theory via writing your own dependent type checker. And then there's a chapter on both Agda and Coq. And there's a really cool thing that he does for Agda, which is ASCII casts. So let's see. Here's an ASCII cast. It's like a video, but you can sort of highlight the text in the video. So what it actually is it's a recording. This is a terminal emulator written in JavaScript, and it records all of the things that would let you modify the terminal. And then you can change the speed at which it's played. And so you can basically see live Emacs interaction sections. And this isn't a video, it's an ASCII cast. You can actually highlight and copy text from it. And then you can see all the commands that Prabhakar is pressing here. So I think that's really cool that he had ASCII cast. So the section on Agda is also like a good, useful Agda tutorial. And then at the very end of it, he recently added a chapter on how to do dependent unification and how to do holes in the presence of dependent type theory. So I'm going to link that in chat as well if I haven't already. And that is, yes, I've linked it in chat already. Oh, yay, someone says that Prabhakar's notes are also, yes. So Prabhakar is a good friend of mine. We've exchanged hundreds of emails, and we've met up a bunch in person, and he was a professor for 2 of my undergrad intro CS courses, and then I sat in on his type theory course as well. Yeah, so here is one more endorsement for Prabhakar's notes in the chat. I really think that like sort of everyone needs to read them. They're great.
So we have a couple of Agda questions.
Yeah.
One of them says, could you do the last proof without using a predefined app by inlining it? And they mean inlining.
Oh, let me make this full screen. Okay, so the question is without using an app by inlining it. Well, in Cubicle, I know how to do this. In Cubicle, it would be pretty easy. The problem is, well, so if this were Cubicle Agda, then I just use an interval variable and it would be very easy. But I think fundamentally, there is a necessity to do what is called a path induction. In other words, match on reflexivity in order to define app. And I think that you could write a where clause and then you could define app here from scratch. But that induction on reducing to reflexivity is necessary unless you're doing Cubicle Agda. Is that the right answer, Amy?
You could also put the recursive call in a with clause and match from that. But yeah, you have to use a pattern matching definition. So
right.
So I could write. Go ahead.
So I could write with, and then I could write the recursive call, map comp fg x's, right?
Mm-hmm.
And let's say that's P. That's going to be a proof of something. So P is a proof of this assertion, the recursive call, and I'm going to match P on reflexivity. Now, the problem is that with is actually very annoying in Agda, so I'm not sure if this is going to work.
That looks like a without K problem.
Yeah. And without K problems are actually usually reasonable, and there's usually a very good hot reason for them. So this is what we'd like to try, but it doesn't work.
Yeah, the short answer is that you have to define app as a separate function or in a where clause, but that's basically a separate function.
And the app is like the thing from Hot that's like you take a path and you get a path in the
so let me just go to the definition and let's look at the type signature of this. So given a function and given an equality, you basically apply the equality to the function.
Right.
Sorry, the function to the equality.
Another question is, for instance, in the proof that minimum is commutative, Martin's proof, because there's a where IH. The type is the successor of the minimum of. Okay, it's probably better if you look at the chat. I'm not gonna say all of that.
Oh, okay. Sure. Whoops. Where is the example with min? App suck inductive hypothesis. So where does Martin prove that example? I guess it's beside where min is defined, right? No, min is only defined here. So in the min commutative example, I guess we didn't do that. Sorry, what's exactly the question? Oh, I see. Fine. Do you just want me to do this example? I'll do this example then. Wait, where is the example min is commutative? Oh, it's below, right? Oh, max is commutative. Oh, I see. There's a proof that max is commutative. Okay.
Yeah, so there's the.
Yeah, so I don't like this where statement. That looks pretty silly. Basically, you're doing a recursive call and you're doing an app. So if Martin expects you to write it like this, then that's pretty silly. What I do is I just look at what the recursive call is, and the recursive call do I want to reduce on both arguments? Let's say I'm going to look at NM and look at what that gives me. And you can see that if I just remove the suck from both of those arguments, then I have this equality and I want to prove an equality between the successors. So I'm just going to app the function suck and I don't even need parentheses, onto this.
One thing.
And I think I actually.
Go ahead.
Well, it's the right type, so it fills.
So I was just gonna say there has been other questions in the chat too about like when when we're gonna get app defined in lecture, and one thing that we haven't even defined the identity type yet. So
Right. So sorry.
so
I
that's
might
one
have,
thing that maybe is worth mentioning to some of these questions.
Yeah, the
Good.
identity type in hot lectures will come up on Monday, if I remember right. From
I
the
think that's
spoilers
what.
Yeah.
I think
The
that's what.
spoilers that we got at the tail end of Martin's lecture. Tomorrow's hot lecture will be about inductive types, and then Monday's lecture will be about the identity type. So that's where we're going to see REFL, app, concatenation, inverses, all that stuff.
Right.
I
had
can
a
answer
question.
one more question. And then because I made a mistake. I signed up to teach a differential equations course in the summer. And I have 3 times a week, 3-hour lectures that I have to grade stuff and a bunch of other stuff. And today's the second lecture. And I also don't know anything about differential equations. So I have to teach myself all the material in 3 hours until the lecture. So one more question and then back to cramming for Ds.
Somebody had unmuted themselves. Please go ahead.
Yeah, so I had a question about AP. Is this applicative, like similar to applicative in Haskell?
No, it's wait, Amy, do you want to answer that?
Sorry, I didn't understand what you were asking the question about.
So the function really looks like applicative type class in Haskell. I'm not sure if that makes any sense, but yeah.
Which function? Sorry,
AP,
the map
AP.
function.
Yeah,
App. Oh, right. So it's Haskell has a function called app. It's the less than star greater than operator. Did I get that the right way around? But they are mostly unrelated. The app in homotopy type theory has more to do with the functor class. In a roundabout way, which I think Paige will get to on Monday. But if not, I'm happy to talk about it on the Discord.
Thank you.
Cool. Okay, so I am now going to rush off. I'm probably going to take a 20-minute break just to wind down and then cram for differential equations. Such is
Good
life.
luck with the real
I hope
numbers.
everyone enjoyed the session.
Is that what they're about? Probably. Good luck with
And the recording
differential
will be posted.
equations. There was one last question which I can field. Somebody asked why you only have to match the populated cases for when turning one equality into the other. That's because Agda is smart enough to figure out that if you had conflicting cases like true and false or false and true, that would be impossible. So it allows you to omit those cases.
Thanks. Okay. I hope everyone comes to Paige's lecture tomorrow. That should be exciting. Now I'm going to, I guess, yeah. Have a nice day. Bye.